already done all for us. Okay. All right.
Good to go. Awesome. So good morning, everyone. We are UCI Modular Cubesat. My name is Benjamin Sorensen.
My name is Elena.
My name is Arlen.
My name is Dominic.
So you can see us in the team breakdown structure. In total, we have 9 units, which equates to 36 hours per week. But we have 2 volunteers, and even though the volunteers don't have any required hours, they put in their fair share. We make sure of that everyone does their work. Now, what is a CubeSat? For those of you who don't know, CubeSats are nano satellites. They provide a budget alternative to small companies and universities compared to full-size satellites, which can be a couple million or billions of dollars. CubeSats are cheap because they come in standardized units. On the screen is a 1-unit CubeSat. They go up from there, so 1 unit, 2, 3, 4 unit CubeSats. This provides extremely cheap launch costs and really standardized framing, which makes that cheap. So we are going to be developing a 2-unit CubeSat, which you'll hear about during this presentation. Now, for our mission, we want to create a satellite that achieves successful communication and performs a 6-month mission, which will be used to give professors and students the opportunity to send experiments into space. Now, to do this, we need to build a bare-bones satellite, which includes a functioning transceiver. We need to manufacture custom solar panels. We need to integrate current and future payloads. And we need to maintain temperature control for circuit survivability in space. For project resources, we have 2 main professors that are helping us out. First is Professor Mies. He's our project advisor. And second is Professor Wang. He is extremely knowledgeable in solar panels and manufacturing. He's already been a great help, and he'll continue to be a great help. He's willing to help the project. Now, this is a really basic project budget for this year. This doesn't include the entire project budget since we are continuing from previous years. So we've already purchased our big ticket items such as the CubeSat frame and solar cells. So in total, this is $850. This is what we think it might cost. This is we currently have $2,700, so we are over budget, or we have more money than we need. These are just the expected costs, which you'll learn more about in future slides. So a really exciting part is that we are going to be launching. This will be the first satellite that UCI launches. We're going to be launching with Interorbital. That's their logo. We are funded by Boeing and Northrop Grumman to make this possible. Now for kind of the meat of the presentation, the design requirements. Now, in order to launch, this is what a regulatory body will be using as step 1. This is to determine if we are in spec with the unit sizes, a 2-unit CubeSat. We need to satisfy these or we're not launching. For more mechanical requirements, NASA has published requirements and tests that we have to pass in order to launch on any rocket. They go through vibrations, shocks, and thermal cycling. We need to pass all of these if we want to launch. And then here are our specific requirements for mission success, not necessarily requirements to launch. They go over each, so these are the really high level requirements. So we're sending a receive signal at a certain frequency range. Our solar panels need to generate enough power. Our space radiator circuit needs to generate the correct voltage and current, and then our heating element needs to keep our circuits within spec. So for really high-level timeline milestones, we have achieved our first milestone, which was to send and receive data with our mock transceiver. This transceiver is going to work very similarly to our custom transceiver. We achieved that last month. And then our upcoming milestones is we need to manufacture our custom transceiver. We need to manufacture our solar panels. We need to create a working circuit for our space radiator. And we need to manufacture version 1 of our heating element. We hope to have all of these done in time for the poster board presentations at the end of this quarter. And then after that, our following milestone is to transmit, with our custom transceiver, transmit signal across the engineering quad before the beginning of next quarter. Now I'm going to start us off with talking about progress updates with thermal analysis and the heating element. So what we've done so far is I created an STK model to really determine the resistance needed in our heating element to create the power dissipation needed to keep our batteries within spec. The top left is an example of an STK output. It has a wave function of the temperature, and through that we determine the minimum temperature and the maximum temperature and the required power dissipation. We use that to calculate the length area of our wire, which is going to be our heating element. And then we created a mock-up heating element to really conceptualize and see what a heating element really is. It's just resistors creating heat and dissipating that heat. And then we integrated a thermostat control for a heating element to create a feedback loop to maintain temperature. So in progress, we're designing heating coil geometry. If you look at those numbers, they're pretty high, 3.7 meters, 5.5 meters. That's a really long length of wire, so we need to figure out a way to coil that wire in such a way that it fits within the satellite. And then next steps would be to manufacture that heating coil and to test if it's actually dissipating the power we predict. So I'm going to pass it off to Erling to talk about communications.
Thank you. So for our communications, we had two main goals for this quarter. The first was to find a manufacturer that would print our PCB boards for us and also solder on the surface components. And the second was to develop a method for performing signal strength tests and range tests for our transceiver. So far, we've figured out the wiring for our mock transceivers to Arduino, and we've started to write the code in order to send and receive data packages. So right here are some images of the Arduino sketch for both the transmitter and receiver, and we're able to send and receive a short data package between both of them fairly reliably. In progress, we're still updating our code, so trying to make sure that it's using GFSK, which is a modulation mode for our transceiver. And then we're looking for software that can perform signal strength tests. Right now, we're tentatively going with SDR Sharp, which can pick up the 438 megahertz that our transceiver transmits at, and also has 3 decimal place accuracy for frequency. Yeah, so we've also we've also found 2 companies that can solder on surface components for our PCBs, and we've already decided on the manufacturer for our PCB design. Our next steps are going to be developing a method for uplink. So we need to be able to tell the transceiver when to start downlinking telemetry. So we can clear the airwaves if necessary, if that's required by the ISS. So we need to be able to tell the transceiver when to start sending it down. So that's what we're going to be working on next quarter. And also performing the range and signal strength tests with our ground station, which we have here at UCI.
So now let's do about thermal management. So the main objective of the thermal management team is to incorporate our load, which is emissivity sample, into the main Cubesat circuit. To do so, we needed to build a circuit that meets the emissivity sample operating requirements. So basically, it should be able to produce the voltages of -1 and 0.5 volts while connected to the Arduino. You can see from the schematic that we already designed the circuit, but the first testing revealed that it's not producing enough current in order for the emissivity sample to operate. So we added a transistor to it, but here is a huge voltage difference between the base and collector. And while we try to add the voltage divider in front of the collector to reduce the voltage difference, it's not enough current. So we're trying to balance it out right now. Our next steps are to continue testing. And when the desired results are reached, we're going to order the PCB and connect the emissivity sample circuit to the heating element. And now Dominic is going to talk about solar panels.
So our main goal for these solar panels will, as you saw back in the requirements, would be to supply around 970 milliwatts to our Panasonic 3400 milliamp lithium ion batteries. And the solar cells that we'll be using are gallium arsenide triple junction cells from TriSolX. And so far, we at the beginning of the quarter, we finished our design of the PCB in software Autodesk Eagle, and we had them manufactured and shipped to us. And we also recently tested the individual solar cells to make sure that we're getting the desired voltage and current output shown by the data sheets. Currently, we are seeking through methods to manufacture these solar cells. We plan on either using a method of applying solder paste and placing them in an oven, or using superconductive epoxy glue for the top terminal, which will be exposed to radiation. The next steps going into the end of the quarter would be to conduct power output testing for the entire solar circuit as a whole. And if we have time near the end of the quarter or going into the next quarter, we will implement a method to control the solar panel output in order to prevent battery damage.
Thanks for sticking with us. It was a little bit long, but are there any questions?
Any response?